Signals and Systems, Laplace Transforms, Part 2. Series on Signals and Systems, Lecture number 4.12. Laplace transforms, like any other transform, they are useful to convert a signal from one domain to another domain, time domain to frequency domain, or frequency domain to time domain. These are Laplace transforms, widely used in the analysis of systems, in the analysis of circuits. In the present session, the focus is on properties, important properties of Laplace transforms. We go a little bit deep in understanding the properties of Laplace transforms in this session, and then we also consider some common signals we encounter in the analysis of systems where we need to know their Laplace transforms. Now, with this small introduction, we move to the session proper. We begin the session by recollecting the definition of Laplace transform. There are two types of transforms: bilateral or two-sided transforms. Another one is unilateral or one-sided transform. Bilateral transform is hardly used. It is the unilateral or one-sided transform that is used widely. When we say Laplace transform, it refers to unilateral or one-sided transform. Here definitions are given. Bilateral Laplace transform of a time domain signal f of t. It is indicated as f of s, and it is equal to, by definition, integral minus infinity to plus infinity f of t e power minus st dt. This is the definition of bilateral Laplace transform. Below to it you can find the definition, defining relation of unilateral transform. Expressions are almost same except for one difference, that is lower limit on the integral sign is 0 minus. So if the integration is from 0 to infinity, it is unilateral. If integration is minus infinity to plus infinity, then it is bilateral. These two are forward transforms. Convert time domain signal into frequency domain signal. Now, after forward, we consider the definition of reverse transform, which gives time domain signal from frequency domain signal. F of t is equal to 1 by 2 pi integral j is there, 2 pi j. Integral sigma minus j infinity to sigma plus j infinity f of s e power st ds. Before going further, one or two points regarding the benefits of Laplace transforms. They convert to transform integral convolutions and differential equations into algebraic equations. Algebraic equations are always easy to deal with when compared to integral equations or differential equations. As transforms convert integral and differential equations into algebraic equations, they make our work simple, easy, less difficulty. Second point is there, it gives the relation between Fourier transform and Laplace transform. Laplace transform is a more general form, and Fourier transform is just a special case which can be obtained by letting s equal to j omega in Laplace transform. Note s stands for complex frequency. In general, it is equal to sigma plus j omega. Sigma is a real part, j omega is imaginary part. Omega is real frequency. Sigma indicates attenuation. Sigma plus j omega, it is S. S is complex frequency. By this time already known to you that S is transform variable as far as Laplace transforms are concerned. Now properties. Laplace transform property. We begin with the linearity property. In simplest possible terms, linearity means obeying superposition principle. If a transform or a system obeys superposition principle, then we say it exhibits linearity property. Mathematically, it can be stated as Laplace transform of a of x of t plus b of b y of t is a x of s plus b y of s. Here a, b are constants, x and y are two signals. In word form, it can be stated that the linearity property states that the Laplace transform of a weighted sum of two signals is equal to the same weighted sum of individual Laplace transforms. Proof is trivial. Same weighted means on left hand side in time domain, x is weighted by a. Right hand side in frequency domain, x of s is weighted by the same amount a. Similarly, y. In time domain, it is weighted by b. In frequency domain also, it is weighted by b. Now we move to another property, scaling property. Here it is time scaling. Laplace transform of f of at is 1 by a, f of s by a. A is positive. In case of bilateral transform, scaling property can be stated as f of at. Its Laplace transform is 1 by mod a, f of s by a. Notice small f denotes time domain function, whereas capital F denotes its Laplace transform. Now, how these two properties are one property, one relation for unilateral transform, another relation for bilateral transform. How these two relations have come into being? It is explained here. For a positive real constant a, Laplace transform of f of at is integral 0 minus to infinity f of at e power minus st dt. Let x equal to at. Then for positive real constant a, Laplace transform of f of at is equal to 1 by a integral minus infinity to plus infinity f of x e power minus s by a into x dx. This can be identified very easily without any difficulty as 1 by a f of s by a. Now we consider another property, time shifting property. Laplace transform of f of t minus t naught is f of s e power minus s t naught. Here t naught is positive. T minus t naught. With the t naught positive, it implies the function is delayed. It is associated with the time delay. Another statement is also there. Laplace transform of f of t plus t naught is e power s t naught f of s minus integral 0 to t naught f of t e power minus st dt. Here t naught is positive, but it is t plus t naught plus, therefore it is time advance. These two are statements pertaining to time shifting property of Laplace transforms. Now let us see how these two properties come to have by Laplace transforms. Laplace transform of f of t minus t naught. It is 0 to infinity f of t minus t naught e power minus st dt. Letting t minus t naught as x, Laplace transform of f of t minus t naught becomes integral minus t naught to infinity f of x e power minus s x plus t naught dx, which is equal to integral minus t naught to 0 f of x e power minus s x plus t naught dx plus integral 0 to infinity f of x e power minus s x plus t naught dx. Here the integral has been split into two parts. One integral from minus t naught to 0, another integral from 0 to infinity. The first term is 0 for causal signals, giving the first relation, this one. To get the second means 1 for time advance. Consider Laplace transform of f of t plus t naught. By definition, it is equal to t naught to infinity f of x e power minus s x minus t naught t dx. A little bit of manipulation shown here. This manipulation involves splitting the range of integration into two, 0 to infinity, 0 to t naught. One can arrive at e power s t naught f of s minus 0 to t naught f of t e power minus st dt. Next property is frequency shifting property. Mathematically, it can be stated as Laplace transform of f of t e power minus s naught t is f of s minus s naught. This relation can be derived from defining relation of Laplace transform. How? Laplace transform of f of t e power s naught t is integral 0 to infinity f of t e power s naught t multiplied by e power minus st dt. This can be seen as f of s minus s naught. We move on to another property known as frequency differentiation property. According to this property, Laplace transform of minus t power n f of t, it is nth differential of f of s. To get this relation, we use the defining relation of Laplace transform. F of s is equal to integral 0 to infinity f of t e power minus st dt. Now differentiate this relation both sides. df by ds equal to d by ds integral 0 to infinity f of t e power minus st dt. Changing the order of differentiation and integration, we can get df by ds equal to Laplace transform of minus t f of t. When differentiation in frequency domain is once, then power over minus t is 1. We can see if differentiation in frequency domain is twice, the power on minus t in time domain is going to be 2. If differentiation is n times, then power over minus t in time domain is going to be n. Hence, the relation Laplace transform of minus t power n f of t is nth differential of. Now time differentiation property. Laplace transform of nth differential of f of t is long expression s power n f of s minus s power n minus 1 f of 0 minus s power n minus 2 1 0, like that, so many functions. To get this relation, consider differentiation of f once with respect to t. Then we have its Laplace transform as integral 0 to infinity df by dt e power minus st dt. And integrating this relation by parts results in two terms. One term is f of t e power minus st, 0 to infinity. Another term is s into integral 0 to infinity f of t e power minus st dt. The quantity f of t e power minus st goes to 0 as t tends to infinity. Hence, we are left with Laplace transform of df by dt is equal to s f of s minus f 0 minus 1, which is given as the second statement of time differentiation theorem. First statement is for nth differential of f, whereas second statement is first differential of f, its Laplace transform. So now, after obtaining this relation, one can extend this process to nth derivative. If the function is causal, f of t is 0 for t less than 0, and f of 0, f prime 0 minus f n minus 1 0, these are all zeros, and the time differentiation property becomes Laplace transform of df by dt becomes sfs, and Laplace transform of nth differential of f becomes s power n fs. Now we consider another property, time integration. Statement is integral minus infinity to t f of tau d tau is Laplace transform of this integral is f of s by s plus f minus 1 of 0 by s. Using definition and integration by parts, definition of Laplace transform and integration by parts, one can find Laplace transform of integral 0 to t f of t dt as two terms. First term is minus e power minus st by s integral 0 to t f of t dt 0 to infinity, plus second term is 1 by s 0 to infinity f of t e power minus s. Is two terms. If f of t is an exponential order function, the first term on the right hand side becomes 0. This fellow becomes 0. You are left with only this. Therefore, integral 0 to t f of tau d tau becomes equal to f of s by s. Notice this can be identified as f of s. 1 by s is already there, so it becomes f of s by s. Here it should be Laplace. L is missing. So Laplace transform of 0 to t over integral f of tau d tau is equal to fs by s. If the lower limit is minus infinity, then integral minus infinity to t f of tau d tau becomes equal to integral minus infinity to 0 f of tau d tau plus integral 0 to t f of tau d tau. So f minus 1 0 minus u of t plus integral 0 to t f of tau d tau. Now it can be written as Laplace transform of integral minus infinity to t f of tau d tau becomes equal to f of s by s plus f of minus 1 0 minus by s. The result can be generalized to higher integrals. Note that for causal functions is f minus 1, f minus 2, f minus n, they all become zeros. Another property, frequency integration property. It means a Laplace transform of f of t by t is equal to integral s to infinity f of s ds. Using the definition, integral s to infinity f of s ds is integral s to infinity integral 0 to infinity f of t e power minus st dt ds. When we do integration with respect to s, we will be getting minus f of t by t e power minus st, limits s to infinity. It gives us integral 0 to infinity f of t by t e power minus st dt, which is Laplace transform of f of t by t. Another property, time convolution. Laplace transform of convolution of two signals f1 and f2 is product of their Laplace transforms. This is time convolution theorem. How it is arrived at? Procedure is apply Laplace transform to convolution of f1 and f2. It gives us integral minus infinity to plus infinity e power minus st, integral minus infinity to plus infinity f1 tau f2 t minus tau d tau dt. It becomes equal to integral minus infinity to plus infinity f1 tau multiplied by integral minus infinity to plus infinity e power minus st f2 t of t minus tau dt d tau. This can be manipulated a little bit, giving integral minus infinity to plus infinity f1 of tau into e power minus s tau multiplied by integral minus infinity to plus infinity e power minus s t minus tau f2 of t minus tau dt d tau can further be manipulated to give integral minus infinity to plus infinity f1 of tau e power minus s tau f2 of s d tau. This integral can be identified as product of two frequency domain signals f1s and f2s. Next, we consider Laplace transforms of certain signals. Common signals are standard signals under Laplace transform pairs. First one to consider is impulse, unit impulse function. Laplace transform of unit impulse can be found equal to 1. It is not at all difficult to have this result. Apply basic defining relation. Laplace transform of delta of t is integral 0 to infinity delta of t e power minus st dt. It comes out to be easily 1. Next signal we consider here is Laplace transform of unit step function u of t. It can be shown its transform is equal to 1 by s. To find this result, use basic defining relation. Laplace transform of u of t is integral 0 to infinity u of t e power minus st dt. It is equal to 0 to infinity e power minus st dt. Now integration can be done without any difficulty. It results in 1 by s. Another signal we consider t power n u of t. Laplace transform of t power n u of t can be shown as n factorial by s power n plus 1. How to get it? Here the procedure is given. It requires applying frequency differentiation property to step function transform. Another function t power n e power at u of t. Its Laplace transform can be found equal to n factorial by s minus a power n plus 1. This is just an expression of frequency shift property applied after frequency differentiation of step function transform. Now, trigonometric functions. Laplace transforms of trigonometric functions. Causal trigonometric functions. Laplace transform of sine omega naught t u of t can be shown equal to omega naught by s square plus omega naught square. One can get it very easily with the help of Euler's identity. Sin omega naught t, it can be written as 1 by 2j e power j omega naught t minus e power minus j omega naught. This is Euler's identity. Of course, for cos, it is same except plus sign in between exponential function. So Laplace transform of sin omega naught t becomes equal to 1 by 2j Laplace transform of e power j omega naught t minus Laplace transform of e power minus j omega naught t. A little bit of manipulation gives us Laplace transform of sin omega naught t as omega naught by s square plus omega naught square. Similarly, for cos omega naught t u of t, one can find its transform as s by s square plus omega naught square. After trigonometric functions, we consider hyperbolic functions. Laplace transforms of sin h, cos h. Following the pattern similar to trigonometric functions in the earlier slide, one can get the transforms of hyperbolic functions too. Express them in exponential form and then Laplace transform can be applied easily. First, we have to express sin h, cos h in exponential form. The relations are given here. Sin h at is half e power at minus e power minus at. Cos h at is half e power at plus e power minus at. With this, we come to the end conclusion of this session. Before closing, let us recollect various aspects of transform properties that are considered in this session. We started properties with linearity, with shifting, time shifting, with and then we moved to time shifting, time scaling, time differentiation, frequency differentiation, time integration, frequency integration, time convolution, frequency convolution, etc. And then we considered Laplace transforms of certain common standard signals like impulse function, step function, trigonometric functions, and hyperbolic functions. Hope this session is useful to you. We meet soon in another session with a new topic.